Okay, hi everyone. So I guess I'll have to introduce myself. So I'm Serge Kas Hanna. I am a junior professor at I3S. I work on channel coding in general and recently applied to DNA data storage. Okay, so in this presentation I will start with the general motivation on why are we interested in channel coding in DNA data storage. And then I will go through some basics in channel coding and then talk about codes for correcting insertions and deletions and conclude with some perspectives. So let's start by going over the encoding and decoding procedure in DNA data storage a bit. So we typically start with some binary file that we want to encode in the form of a collection of short DNA strands. The reason why we want these strands to be short are because of synthesis limitations, as we have discussed throughout the school. And this encoding actually involves a lot of steps in general, including source coding, which was discussed this morning, indexing, formatting. Some of these steps are optional, others are not. So you have to fragment your binary data because you want to store them in a short format. And then there's channel coding here. This is part of the story. Once we have our short DNA strands, we synthesize them. Wait. Okay. We synthesize them, we store them, and then we sequence them. And at the output of the sequencer, we have a bunch of noisy, shuffled reads. They appear in some random order, and they have some insertions, deletions, and substitutions within them. Then we go to the decoding part, which is also a multi-step process. Typically, you cluster your data, you align them, you derive some consensus sequence, and then you do channel decoding. So this is to say that channel coding and channel decoding is part of a bigger picture when it comes to encoding and decoding in DNA data storage. And I will focus today on this part of the encoding and decoding in particular. Of course, we saw how DNA storage works, and we know why it's interesting, so I will immediately move to the challenges. One of the main challenges is data reliability. So this is a key challenge in DNA storage due to errors and biases that can occur during various stages of the DNA storage pipeline, including synthesis, storage, sequencing, etc. These errors and biases can lead to erroneous or lost DNA strands. So erroneous, obviously, because you can have deletions, insertions, and substitutions in the nucleotides, and lost because of the bias. Sometimes you have like amplification bias. Some molecules get amplified more than others, and this bias can become even worse when you sequence the data. So you will have an unequal representation of the data you have. Now let me move to the general types of errors that we have in error control coding. First, there are erasures. So erasures is one type of errors. So let's say we have this initial data, and these nucleotides underlined in red are erased. In this case, they are replaced by some unknown symbol on the other side. So for erasures, we actually know the positions of the errors, but we don't know their value. Then the second type is substitutions, where some of our symbols get substituted by other symbols. So in this case, we don't know the position of the errors, but if someone told us what the position of the error was, we can infer something about their value. Imagine that this is binary. If you know that there's an error at position 2, then you just flip it, right? So substitutions are more challenging than erasures in this sense because you don't know the position of the errors. And then to our lovely deletions and insertions. When you have deletions, these two symbols are completely removed from the sequence. And when you have insertions, new symbols appear in your sequence. So your sequence is actually shorter or longer now. And in this case, you don't know neither the position nor the value of the errors. And this is why deletions and insertions are the most general and challenging types of errors to deal with. For instance, a substitution can be viewed as a special case where a deletion is followed by an insertion at the same position. So this is just a special case of the more general deletions and insertions. So in DNA data storage, what type of errors do we experience from these general types of errors? We do experience deletions and insertions and substitutions at the base level, at the nucleotides, and we also experience erasures at the strand level because some of the strands are lost. And for us, if we indexed these strands and we know that some indices are missing, then we know that there were errors there. So this translates to erasures from the point of view of error control coding. So we have all of these, but at different levels. So some at the base level and some at the oligo level, entire oligo being lost. Okay, so why do we want to do channel coding? So these errors and biases can be mitigated using channel coding techniques. And channel coding techniques, in short, is the practice of adding redundancy to your data. You add redundancy in your data in a way that you can exploit later on to provide robustness against errors and biases. This is a small example that we will be revisiting later on. This is what we call a two-layer channel code. So imagine that we have these uncoded strands, and one thing you can do is you apply an outer code which adds additional oligos in your pool, and then you apply an inner code which adds redundancy within each oligo. So this is why it's called a two-layered structure. So then in the end you have some coded strands which contain redundancy. So the redundancy is highlighted in green and blue. So this is the practice of adding redundancy to your data, and we will discuss how we can exploit this redundancy to mitigate errors and biases. Now, what channel coding offers? So it first offers improved reliability because it increases the probability of successfully retrieving your data. I think I don't need to convince you a lot about that. Then it can result in reduced coverage requirements. So we can sometimes or often recover our data with less reads if we use channel coding techniques. And that translates into more speed, right? So less reading cost in terms of speed, and it could also translate into less reading cost in terms of money depending on what kind of sequencing you're doing. And it can also enable the correction of systematic synthesis errors. This is something we saw in Yannick's presentation. So sometimes we have systematic synthesis errors. In this case, these errors appear in all your reads. So you can read as much as you want. You can read it 100 times, 1,000 times, 1,000,000 times. Just by the practice of reading more, you will not be able to correct these errors. But with channel coding, you can. And last, and in my opinion, the most important one, is it can contribute to reducing the costs of DNA storage. Let me explain how. So one of the reasons why synthesis is very expensive nowadays is because companies put a lot of effort into producing almost perfect oligos. But what if we tell them, relax, like you don't need to have almost perfect oligos for DNA storage applications at least. We can handle these errors algorithmically. You don't need to worry about them at the biochemical level. And in that case, probably they can provide a lower cost for synthesis. And this is something you could do today. For instance, you have different synthesis providers. Some are less expensive than the others, like GenScript is less expensive than Twist. And lower cost in life in general translates to lower quality or correlates with lower quality. So if we can deal with lower quality synthesized oligos because of channel coding, then we would indirectly decrease the cost of DNA storage. But nowadays, for instance, people still go to Twist when they want to do a DNA storage experiment. Why? It's because they don't want to handle these errors, or they're not confident that they can handle these errors. But if we can handle these errors, then this would enable the use of lower cost and faster synthesis technologies, and this is why it can correspond to reduced costs in general. Okay, this is the motivation in general about channel coding. Now I will go over some basics. Okay, so as I said, and I will repeat, so channel coding is the practice of adding structured redundancy to data and leveraging that redundancy to achieve robustness against noisy or imperfect system conditions. Let's go over some forms of channel coding and some toy examples. Constraint coding, which we saw this morning, can also be viewed as some form of channel coding. Why? It's because we're adding redundancy. As long as you're adding redundancy, it's channel coding. So let's say we want to encode this binary data into DNA to avoid homopolymers. You can go with the unconstrained mapping, where every 2 bits maps to one symbol, and then these bits will become AAAGT. So you have a homopolymer here, right? So in this case, you couldn't avoid homopolymers. But what if you go with this mapping? Every 2 bits maps to 2 nucleotides. And in this example, and in general, with this mapping, you will not have homopolymers. Now you have repeated patterns. You have AG, 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 which is a different problem. But at least for homopolymers, this solves it. Is this the optimal way? No. We saw this morning that we have limits and we have the capacity results. So this is not optimal. This is just a toy example. And for the left side, the rate we have is 2 bits per nucleotide. When I say rate, always think about the size of the input divided by the size of the output of your encoding. So here it happens that the input is binary and the output is DNA. That's why the rate is in bits per nucleotide. And this is the maximal rate, 2 bits per nucleotide. In this case, we have 1 bit per nucleotide with the other method, which avoided homopolymers. So this decrease in rate comes from the fact that we added redundancy. So here we had 10 nucleotides. Here we had only 5. So there's a redundancy here, which translates into decreased rate. So constraint coding is one form of channel coding. Let's go through another form of channel coding, which is error detection. So let's say I want to encode these 4 bits, 0, 1, 1, to detect a single substitution error. I don't want to correct it. I just want to detect that an error happened. So here, what you can do is use a single parity code. So this is my data. I want to add 1 bit to it. What do you think I can do? Well, what bit should I add? Any opinions? From non-experts? I mean, it's a parity bit, right? You can, by definition, you can add these bits, modulo 2. So 0 plus 1 plus 1 plus 1 remains 1, modulo 2. So I add this redundant bit now, right? And now let's say I have a substitution error. The third one became a 0. Now if I want to detect whether an error occurred or not, I just sum these up and see if the sum of the first 4 is equal to the 5th. And in this case, it's not. And that's why I can detect that an error has happened. This is a toy example for error detection. And the generalization of this is what we have in the challenge, which is we have a checksum, which is not only 1 bit long. I think it's 8 bits or 4 nucleotides long. So that's one form of channel coding also.
How do you determine that the parity bit here is 1?
It's just the sum of the 4 modulo 2. So 1 for odd, 0 for even.
Okay.
So here, if you sum the first 4, what you're going to get is different than 1. You're going to get a 0. So that's why you know that there was an error.
So if the first 4 could be an arbitrary combination of zeros and ones, your parity bit gives you 50% resistance against substitution.
So yeah, the first 4 could be arbitrary, but the 5th one is fixed in terms of the first 4. So the 5th one is the sum of the first 4. So it's fixed.
Okay.
And in this case, if you have one substitution error, wherever that error is, even in the parity itself, you can detect it. If you have 2 substitution errors, probably not. But this is why it's a single substitution error detection example. Now to the third form of channel coding. And by the way, here the rate is 4/5. Let's always keep the rate in mind because we had 4 and we mapped it into 5. size of input divided by size of output. So it's 0.8. It's less than 1 because we had redundancy. Let's move to the third form of channel coding, which I like the most, is error correction. Let's say I want to encode 0, 1 to this time not detect whether an error happened. I want to actually correct the error. So in this case, we only detected the error. We were not able to correct it. So the most trivial way to do it is to do what we call repetition coding. And this happens in life. If I say something now and you don't hear what I say, you just tell me repeat. So we're going to repeat each of these bits 3 times. So 0, 1 will be mapped into 3 zeros and 3 ones. This is what a 3-fold repetition code is. Now, if I have one substitution error anywhere, but in this example, it's the second, how would I use this redundancy to correct that error? Any ideas?
Majority voting.
Exactly, majority voting. So I do majority voting over windows of size 3. So in the first 3, I have 2 zeros and a 1. I decoded a 0. And then in the last 3, I have 3 ones, so obviously it's a 3. And if I do majority voting, my error is corrected.
And 3 is an arbitrary number that you picked, right? Obviously, if you have more of it, the chances of, like, there's better chances of error correction.
That's a good question. So 3 is enough to correct 1 error. 5 would be enough to correct 2 errors. 7 would be correct with 3 errors. So that's a nice question, yeah. If I do repetition of 5, I can do 2 errors because the majority would still be intact in that case. Yeah.
Does this mean that if you want to record a longer thing for which you expect more errors, you will also need more copies?
Yeah. If you use this trivial repetition code, yeah, that would be the case.
So the problem explodes somewhat exponentially, non-linearly.
It's linear, so the redundancy you have is a linear factor of. So here we tripled our input. If you want to do 2 errors, you would multiply it by 5, etc. But anyway, this is the most trivial error correction code, which is not efficient. But it serves as a toy example for you to know what channel coding is in terms of error correction. And the rate here is 2 over 6, because the input was 2 and the output is 6. And you can notice that the rate is less than the rate for error detection. So error correction is more difficult than error detection. Okay. Now, so while I was preparing this presentation, I was thinking if I were to explain one efficient error correcting code, not a trivial one, which one should I choose? And then I thought I would have a survey and ask you, what code have you most heard about? What's the most famous code among the audience here? And then depending on the result, I will explain that code. Okay, so let's go over the possibilities. So what is the most famous code among the participants here? Wait, we have options. So how many of you have heard about polar codes? 1, 2, 3, 4, 5. So polar, 5. How many of you have heard about LDPC codes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many of you have heard about Reed-Solomon codes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How many of you have heard about BCH codes? 7. 7 for BCH. Raptor codes, I'm not going to count, but this is less than Reed-Solomon. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 for Raptor. That's impressive. What?
It was mentioned just before lunch.
Oh yeah, but I was assuming this is the knowledge you had when you came to the school. So. And one last thing, read Muller codes. 7. Okay, this is also impressive, read Muller 7. Okay. So we will explain read Solomon codes. And it didn't really matter what you knew. I would have explained read Solomon codes anyways. So let's do read Solomon codes. I will try to explain read Solomon codes in 3 slides. And I'm expecting that most of you could follow these 3 slides. Okay, so the core intuition behind read Solomon codes is it can be grasped with high school level math. And a first intuition on read Solomon codes is reconstructing a line from points. Let's see how. Suppose we want to store 2 numbers, a and b, which are 2 and 1. Let's define a line using these numbers. Y equals 2x plus 1, which is this line you see here. Now, instead of storing 2 and 1, I will store evaluations of this line at distinct x values. So for x equals 0, 1, 2, 3, 4, I will evaluate this line and store the evaluations. This means that at 0 we have 1, at 1 we have 3, at 2 we have 5. I'm evaluating this line at several x's. So to encode this message, which was to 1, I'm storing these evaluations of this line, 1, 3, 5, 7, 9. Is this clear for everyone? Yes?
Does it mean that your software knows that you're evaluating for x equals 0, 1, 2, 3, 4, which is why you don't need that part?
Can you say that again?
So you input 0, 1, 2, 3, 4, and then you get the code where they are. Does it mean that your encoder and decoder knows that you always go 0, 1, 2?
Yes, there's a specific order, a specific assumed order in which these points are evaluated. That's a good point. So now I encoded this message into 5 numbers.
Is there a reason for picking 5 numbers?
No, it's arbitrary. And the rate, in this case, it's 2 over 5, because the input is 2 and the output is 5, so the rate is 0.4. So why is this now robust to errors, this encoded form of the message? Let me ask a question. So let's talk about a specific type of errors, erasures. So if I have these 5 symbols stored and some of them get erased, like in this case, I told you about erasures, they get replaced by some unknown symbol. So let's say the first, the third, and the 5th symbols were erased, 3 erasures. And I see the 3 and 7. Can I still recover my message? Why? How many points you need to evaluate a line? Any 2 points are enough to evaluate a line. So if I see 3 and 7 at positions 2 and 4, then I can use these to find the equation of the line. And once I have the equation of the line, I have the slope, what we call the slope and the y-intercept, a and b, and then these are my message, because I encoded my message into the slope and the y-intercept of the line. Okay, let's talk about substitutions. Can we also correct substitutions, not only erasures? So let's say I have a code word, the same code word, and then the third number was supposed to be 5, but it was substituted by 2. So I'm looking at something like this. These are the valuations I see. So can I still decode? The answer is yes, because the majority of my evaluations belong to a given line, which is still the same line. And then by doing that, which is sort of similar to majority voting, but in a different sense, I would be able to reconstruct this line and correct. Yes, Vasily?
Do you also have an additional layer of robustness because you're expecting the numbers to be ordered from in a decreasing or in increasing fashion depending on your slope?
No, that was arbitrary actually. So I'm not using the fact that they are sorted from least to largest, if that's what you mean. But
I mean, in your linear example, if if you see a guy that's not fitting that pattern, you know that something is wrong.
Yeah, that's a good point. We didn't use that here, but in general, I guess it could be used. But the idea is that, as I will explain later, Reed-Solomon codes are defined over modular arithmetic. So this means that you won't have always an increasing numbers. If you do modulo 5 or modulo 7, then some numbers are gonna, but we'll get to that. So here we can decode, yes. Okay, again, we were able to correct one substitution. Let's go to the second slide and the second intuition on Reed-Solomon codes. So the core idea, as you saw, store structured data so that the original structure can be reconstructed even if some of the stored pieces are unreliable. For encoding two information symbols, the structure can simply be a line, as we saw on the previous slide. But how do you generalize this? What if we need to encode more than two information symbols? What if we need to encode k information symbols? What structure do we need? Any ideas?
Can you keep on adding dimensions?
Can you say that again? I didn't hear you.
Can we keep on adding dimensions?
What?
I mean, you gave us a line, you can do a plane for 3 points. I'm not sure what you call a 4-point thing.
We call it a polynomial of degree k. So yeah, a polynomial of degree 1 is a line. So in this case, the answer is correct. So we can have a polynomial of degree k minus 1 if we want to encode k symbols. And you would encode the message symbols as the coefficients of this polynomial. Any question?
No, it's fine. No.
Yeah. So let's say this is our ugly polynomial, and it's f of x equal m0, m1, m2, m3, m4, x4. And we want to encode this message into a code word. So the message is of k symbols, and the code word is of n symbols. So the redundancy is n minus k. We add n minus k extra symbols. So I shouldn't, I was supposed to ask a question. So what should we do? It's the same as what we did before. We should evaluate this polynomial at distinct points and store these evaluations. Do you see how this is like similar to what we did with the line? So let's evaluate this polynomial at n different points to produce n encoded symbols. So if you have n different points, let's assume it's 0, 1, 2, 3, etc. If we evaluate this polynomial at 0, at 1, at 2, and store these evaluations, then we get our encoded code word. So this is how we encode, in general case, k information symbols into n encoded symbols. And what is the error correction capability here? So with the line, we needed two evaluations to reconstruct the line, right? With a polynomial of degree k minus 1, how many evaluations do we need? K evaluations. What does this mean? This means that out of the n evaluations, if I lose any n minus k of them in the form of an erasure, I can still recover my message. I'll repeat. So I have n symbols, and k are enough to reconstruct the polynomial. So any n minus k erasures, I'm still good. This is for erasures. For substitutions, it's more involved, but I will give you some insights in the next slide. So the error correction capability stems from the fact that we only need k correct evaluations to reconstruct a polynomial of degree k minus 1. I don't need all the n. Any questions about this? Okay.
Here we're assuming that there are only like k possible, like if there are more errors than
You would agree is n. So the redundancy I'm adding here is n minus k. If I want to address, let's say n minus k is 5. If I want to correct 10 erasures, I would add 10 additional evaluations. So it's the same question, kind of what you asked about the repetition. The more you add redundancy, the higher error correction capability you have.
No, but you don't start out by knowing how many you need to add, right?
No, you just decide what you want to do, and then depending on what you designed, you will have a certain performance. You will still have some cases where you are not able to decode. So channel coding in general is not a zero error thing. So sometimes you can fail, and that's fine if the probability of that is small enough. Okay. Now the formal definition is something like this. So the code is constructed as polynomial evaluations at n distinct points. Now one thing I was throwing under the rug when I was explaining before, and I will talk about some facts about Reed-Solomon codes. Why do we love them? And are they enough for DNA storage? So one thing I missed intentionally is that Reed-Solomon codes are defined over what we call finite fields. It's hard to explain finite fields right now, but you can think of it as a finite set of elements over which basic arithmetic operations are done modulo q, and addition, subtraction, multiplication, division are well defined. So all this computation I was explaining before, we do it over a finite alphabet. So that's why I talked about the modular thing. So q is the number of elements I have in this set. So if I have q elements in my set, I can only have q distinct evaluations, right? And this means that if I want to construct an nk Reed-Solomon code, my field has to be large enough and should be greater than or equal to n, because I need n distinct evaluations. So at least I hope I have n distinct points in my set. Okay? Why are Reed-Solomon codes popular and why do we love them? It's because they have optimal error correction capabilities. So they achieve what we call the singleton bound with equality. Let me explain what does that mean. So in general, any nk code, the minimum distance of that code, which defines its error correction capability, is upper bounded by n minus k plus 1. But for Reed-Solomon code, we have equality here. So it's the highest minimum distance you can get, and that highest minimum distance translates to the best error correction capability. So let's talk about erasures, since we mentioned this before. So if I have an nk Reed-Solomon code, how many erasures can I correct? We talked about this like few minutes ago. Based on the intuition that I only need k evaluation of the polynomial. So if I have n, I can afford to lose how much? N minus k. So I can correct n minus k erasures, which is equal to d min minus 1 in this case. The number of substitutions I can correct, I won't explain why, but it's n minus k over 2. This means that substitutions are more costly in terms of correction, and that also is in line with the fact that substitutions are more challenging than erasures. A very nice property is that I can actually correct combinations of erasures and substitutions. It doesn't have to be only erasures or only substitutions. And in this case, I can correct E erasures and S substitutions as long as E plus 2S is less than or equal to n minus k. So here, this 2 factor says that I'm paying double to correct a substitution than what I pay to correct an erasure. That's how you should understand it. So I can correct combinations as long as E plus 2S is less than or equal to n minus k. Now, it's the minimum distance between any 2 code words. You don't need to understand the details of it, but as you see here, it translates to the error correction capability. So if I have a code with minimum distance, whatever d min is, I can correct d min minus 1 erasures, or d min minus 1 over 2 substitutions. So it's some metric, you can think of it, that defines the error correction capability. Okay? So just a flashback that this is a DNA storage school. Reed-Solomon codes are used as outer codes in DNA storage because if you lose some of your oligos, which are erasures, you can correct them. And if you have some residual substitutions in your oligos, you can use Reed-Solomon codes. But the next question I want to ask is, what is the number of correctable deletions and insertions with Reed-Solomon codes? And the answer is 0. So that's why they are, by themselves, they are not good enough for DNA storage. They can help address biases, to be more specific, and lost DNA strands. But in terms of correcting errors within a strand, they cannot address deletions and insertions. That's why we need to go further and talk about indel correcting codes. So Reed-Solomon code is a code that can correct erasures and substitutions, but not indels. This is the takeaway message of this part. Any question before I move to the third part?
But if the insertion is something that is like not falling within your polynomial graph, you could identify it as an insertion.
No, you already have a loss of synchronization because there the polynomial evaluation is assuming that the first point you see is the evaluation at 0. The second point you see is the evaluation at 1. But if you insert something in between, everything to the right of that is already even the evaluations are off. So you would think that the fourth one is now the evaluation at 4, but it's actually at 3. And you have no way of knowing that. So this is what we call loss of synchronization. So it's not only about that outlier, it's going to shift everything afterwards also.
No, that is if it fits into the graph. If it doesn't fit into the graph at all, then you can identify it as...
When you say fit in the graph, you're assuming you know the x values. But even the x values are going to be shifted once you have insertions and deletions. So you're looking at fitting something at the wrong positions even, if you have these insertions. Okay, 20 more minutes. Oh no, I have 1 hour 15. Good. So codes for correcting indels. So now going back to DNA storage a bit and explaining why we need codes to correct indels in DNA storage. A common design strategy is the two-layered code that I explained in the beginning. So we have these uncoded oligos. We add some additional oligos in our pool using an outer code. And then we have redundancy within each oligo using an inner code. So here, the inner code should be a short code, short in length, I mean. Should be a short code capable of correcting nucleotide edits within the oligos. When I say edits, I mean deletions, insertions, and substitutions. So the term edit encompasses all these three. So since I can have deletions and insertions at the base level, I need a short code. Why short? Because the length of the oligo is short due to synthesis constraints. And actually designing short codes is more difficult than designing long codes. This is something that we talked about in the morning also. Now the outer code can be a longer code because you can have like thousands or millions of oligos in your system. So the dimension is actually the vertical direction. So it can be a longer code that can be designed to recover lost oligos, which are erasures, and residual errors, substitutions from the inner code. So what is the state of the art here? So we have many existing codes which are suitable for outer codes, like Reed-Solomon, like LDPC, like Raptor. These codes that many of you have heard about are suitable to be used as an outer code in DNA storage. So they can address the bias issue and correct some substitution errors, but they cannot be used to correct deletions and insertions. So there are very few practical edit correcting codes suitable for inner codes. So we have very few short codes capable of correcting deletions and insertions. And I'm talking at the sequence level now. I'm not assuming I have 10 reads, I do alignment, consensus, whatever. I'll come to that later. I'm just saying at a single sequence level. So this is a bit technical, but let me go fast over this. So the problem of correcting deletion and insertions is a fundamental problem in information theory that goes back to the 1960s, even before DNA storage was a thing. So this is a fundamental problem in information theory, but people look at it from a different perspective. They look at codes which are very long and which have a very small number of errors. So they rely on some asymptotics which do not apply to DNA storage because our strands are short. So that's why there is a long list of experimental work which actually used channel coding as part of their experiment. Some experiments don't use channel coding, but there are some experiments that did use channel coding, and they never used any of these codes from information theory. It's because they are not applicable in DNA storage due to the discrepancy in terms of length. So these codes are long, whereas in DNA storage we need short codes. So these works have not used the insertion and deletion correcting codes. Instead, they heavily relied on sequencing redundancy. So they heavily relied on the fact that you can read the same strand 10 times, 20 times, and then hope to use that redundancy to correct. Yes?
Yeah, so what would be like the length of the oligo that would allow you to go and use this previous one?
So in these assumptions, as Aline said, you take n to infinity. I don't know what infinity is in life, but I would say at least in the order of tens of thousands. So you need them to be at least in the order of tens of thousands to have a moderate rate, like a 0.5 rate, and for it to be able to correct these errors. So there's still a gap, I guess, between 300 and tens of thousands. So yeah. So, but the good news is that there is work that's being done on codes for correcting random deletion and insertions at short lengths. There were some earlier works that could work for tens of thousands, which is kind of not very long in information theory. But there are also works that have designed codes that work for the smaller lengths of 100, 200, 300, but these are very few. So there's the Hedges code, DNA Aeon, and the GC Plus code, which is part of our work. So I will talk today about the GC Plus code because it's easy to explain since you have some background now on Reed-Solomon codes. It uses Reed-Solomon codes, but it's not the entire story. So I will talk about the GC Plus code, try to explain it in a simple example, and then show you some results which compare the performance of the GC Plus code with one of the existing codes, which is the Hedges. So the purpose of this slide to say that it is really an active area of research to design short block length codes for correcting deletions, insertions, and substitutions. So the GC Plus code, this is the code that I've worked on, and it checks multiple boxes in terms of stuff people care about when it comes to channel coding. It's implemented, it's available on GitHub, it's published, that's why I'm talking about it today. I will try to explain it in a simple example. So you were trying to scan it, I can. Okay, so the GC Plus code, I will explain through a one-slide example and then say how this example can be generalized. So this example is going to be in binary because I like binary, and in general it can be generalized to quaternary, and that's what the simulation results will be about, the quaternary results. But this example in particular will be binary. So let's say we start with a 16-bit message that we want to encode. We're going to first divide this message into blocks of size 4. Why 4? Some of you may ask why 4. At this point it's arbitrary. Later I will explain why we chose 4. and then we're going to map these binary blocks into numbers over a certain field. So this is like converting binary to decimal, for those of you who are familiar with that. So 6, 10, 13, 9. So my message now is 4 symbols, but my input is binary. So I will use an 8-4 Reed-Solomon code to encode this into 8 coded symbols. I will add redundancy of 4 symbols. Think of these extra symbols as polynomial evaluations from the Reed-Solomon code we discussed before. But the first 3 parities, I'm going to call them guess parities. That's what the name of GC+ comes from, guess and check. So the guess parities are the first 3, and the last parity was what I call a check parity, and I will explain soon why these parities are classified into 2 categories, because they serve different purposes in the decoding part of it. Okay, so let's say now we have deletions and insertions. So let's say the 6th bit is deleted, so I will map this back to binary, and this is the binary version of what I encoded here. So let's say the 6th bit is deleted, the 13th is substituted, a 1 is inserted at position 15, a 16th bit is deleted, so I added 4 deletions and insertions and a sequence of length 28, which is significant. So this is like a significant portion of errors in a small sequence. And I will explain how we were able to decode these errors in this example. So on the other end, I will get 27 bits. Why 27? Because I had, I guess, 2 deletions and 1 insertion. So the net effect is -1 here. So delta, which is the difference between the length of the encoded one and the received one, is -1 here, because I had more deletions than insertions. So how do we decode this now? So the shift is -1. So I was expecting to receive 28 bits, but I received 27 bits. So there's a shift of -1. I'm going to use that to generate some guesses. So on the first guess, I will assume that this shift occurred in the first block. When I say block, I'm referring to grouping of bits of size 4. So let's assume this shift occurred in the first block. And in the rest, I had no shift happening. This is just a guess. And as a function of this guess, what I will do is I will segment my 27 bits accordingly. So instead of grouping it into 4 bits at the first position, I will group it into 3 bits, because I assumed that at position at the first block I had a -1. So I lost 1 bit. And then for the remaining blocks, I will just map them 4 by 4. Yes?
So here we're using the 7 blocks, which are the initial information plus the guess parities? Okay.
Yeah, that's a good point. I'm omitting the check parity for now. The check parity is further, that's why I was saying that it's not only about Reed-Solomon codes. The check parity is something we need. I will explain why we need it. And it's in practice, or in reality, this is further encoded with an additional layer of error protection, because it's crucial to the decoding procedure, as I will get to soon. But for now, I omitted it, and I'm assuming that I have it and it's correct. So now, after I use this guess to do the segmentation, the block which I assumed that to have a shift of -1, I will treat it as an hypothetical erasure. I will just say I have nonsense there. I will replace it by a question mark. The rest of the blocks, I just map them from binary to decimal, as I did previously. So now I will try to decode this. So I have 1 erasure to decode, at least, with the Reed-Solomon code, right? But in fact, if you compare this to this, how many errors do I have? Forget about the last 2. So I have an erasure at position 1. I have a substitution at position 2. I have another substitution at position 4. Position 3 is correct. 13, 13. But here 3, 9 substitution. So I'm trying to decode 2 substitutions and 1 erasure with a Reed-Solomon code with 3 parities. Do you think I'll be able to do that? No, because of the error correction capability of Reed-Solomon code, which I talked about before. It can correct E erasures and S substitutions as long as E plus 2S is less than 3 in this case, because I have 3 parities I'm using for decoding. So I won't be able to decode this. In other words, I will decode something, but it will be wrong. So this is the message I'm recovering here, because the message is of size 4. But at this point, I'm not sure if this result is correct or not. I mean, I ran the decoder, but I got something. Is it correct or not correct? I don't know. That's where the check parity comes into play. So now I use the check parity to see if this is actually a valid message or not, because the check parity is also a parity related to the other messages. So now I check this against the check parity, and in this case, it's not consistent with the check parity. What does this mean? Now I know that this is a wrong guess. The guess is wrong. So what I do another guess. So in the second guess, I will assume that the -1 shift occurred in the second block. I will do the segmentation again and treat this second block as an erasure. Now, comparing this to this, I have 1 erasure at the second position and 1 substitution at the 4th position. So I have 1 substitution, 1 erasure, which is different than the other case. And now I can handle this with my Reed-Solomon code. So I will decode something, and it will check out with the check parity. And with this, I stop. The second guess worked for me. So now I claim that this is the correct message, and it is actually the correct message. Okay? So now you may say you got lucky maybe with 2 guesses. You were able to do it. In general, you may need a lot of guesses. So actually, the computational complexity of this is a problem. And I will talk more about that later. But at least we were able to correct 4 deletions and insertions in a sequence of length 28, instead of thinking about codes of length tens of thousands or millions or whatever. In general, there's a lot of parameters for this code. So the segmentation length, which we chose 4 in the previous example, is L in general. And the number of guess parities is some C1. The number of check parities is some other C2 parameter. And then you have some other parameter that controls your decoding complexity. And there are a lot of properties of this code in terms of the encoding complexity, the decoding complexity. And in this example, the decoding worked, but in general, it could fail. So the point is to analyze the probability of decoding error of this code. We have a construction, but how good is it? So we have to analyze its performance. And I will show you some results in the quaternary domain, even though the example was in binary, in comparison with hedges. So here we have a message of 168 bits, and we are performing 10 to the power 6 independent trials, and then recording how many successful decoding we had, how many failures we had, and then reporting it the average as the probability of decoding error. I will show you results for the GC plus code, which encodes the 168 bits into 128 nucleotides. So the rate is 1.31 bits per nucleotide. And the results for hedges, which encodes into 176 nucleotides. So it adds more redundancy, and its rate is 0.95 bits per nucleotide. So in comparison, the first case is for symmetric edits. This is for theoretical purposes. I'm assuming that the probability of a substitution is equal to the probability of deletion, is equal to the probability of insertion. That's why it's symmetric edits. And we're increasing the edit probability and comparing the probability of decoding error of the 2 codes. And here you can see that this GC plus code outperforms the hedges by a significant amount. Now you may say that, okay, in practice, it's never symmetric. So let's consider ratios, other ratios. And these are ratios motivated by some experimental results from one of Grass's paper, which says that 53% is substitutions, 45% is deletions, and only 2% is insertions. And for these proportions, we also compare the two, and the difference is still there. Now let's merge these two into one graph. I did this because there's an interesting thing to report here. It's that for the asymmetric case, the GC plus does better than the symmetric case, whereas with hedges it's the opposite. So with hedges, when we have unequal error probabilities, it does a bit worse, slightly worse. So the observation here is that we can have more reliable decoding using GC plus with less redundancy. So even though the redundancy was less, the rate was higher, we were able to achieve better decoding performance, which is something. So, okay, I work in a field where having simulation results is not enough. So, and experiments, I mean, are not always relevant in information theory. So what we like to do is to actually provide theoretical guarantees on the performance of this code. Like do some math and prove that your probability of decoding error is quantified by some expression, like upper bounded by some expression, theoretically. And then compare the theoretical bound to the empirical performance. That's our favorite practice in information theory and coding theory. So there's also work into evaluating the theoretical decoding error probability of this code. For that, the high-level idea is to define 3 problematic events that if these events occur, they can be bad for us. The first event is that the edit errors translate into more erasures and substitutions than the code can handle, than the underlying Reed-Solomon code can handle. The second problematic event is that the actual edit error pattern does not lie within our search space because we're making guesses, right? We can only make a finite number of guesses. Maybe all my guesses were wrong. So there's an event where all your guesses are wrong and the actual edit pattern does not lie within the search space. And there's a third event. What if the check parities are recovered incorrectly? So we were using these check parities that you asked about to eliminate or validate our guesses. What if these parities are wrong? That's another problematic event for us. Then we combine the probabilities of these 3 events using a union bound, which is a bound that we also like. So the probability of decoding error of this code is upper bounded by some function of the probabilities of these 3 events. Now you have to evaluate the probability of each event separately, right? Because of this sum here. So we do some math, we get the probability of event epsilon 1. We do some more math, we get the probability of epsilon 2. We do some more math, we get some other intermediary result we need, and also some more math to get the probability of event epsilon 3. And then if you combine all these, you have a bound on the probability of error that you can actually compute. So let's compute that bound. It's the dotted line here. So this dotted line is the theoretical bound. So this says that your decoding error probability is guaranteed to be less than this dotted line. And empirically, you can see this validated. The blue solid line is below the blue dotted line for the symmetric case and also for the red. So the bound, there's a gap, of course, which is expected, but I think it's okay. It's not a large gap. And having a theoretical bound for such a difficult problem is also valuable, I believe. So I will conclude. Yeah.
Do you, like, so you're defining the 3 possible problematic cases.
Yeah.
Do you also rank them in, like, order of preference in some way?
Rank them in terms of what you said?
So maybe when you solve for problematic case 1, you might end up messing up problematic case 2.
Yeah, that's a good question because you see, like, the probability of error is upper bounded by the sum of these events. So if any of these happen, you're screwed. So No, there's no prioritization. It's the idea is that if any of these events happen, you have an error. That's why the probability that you have an error is the sum of these using the union bound plus some other term. So that's why they accumulate. It's not like the probability of event 1 plus 2 plus 3, because if any of these occur, it's bad. So.
And there's no way that error 1 influences error, like correction of error 1 causes error 2.
There is some, they're not completely mutually exclusive events. They are not unrelated events. But the nice thing, what we call the union type bound provides us, is that you can evaluate a bound by separating these events. Now, if you want to consider what's common between these events and the intersections of these events, you can probably improve this bound. So ideally, you can get an equality instead of a bound if you want to go into all the considerations you're mentioning.
But what do you typically do?
We bound stuff.
Okay. So you're not like aiming to achieve an equality.
No, what I want is to say that my probability of error is less than something. So an upper bound is already good enough for me.
Okay, so you're saying the combination of these errors should be lesser than a certain upper bound that you've defined.
Not should be, I'm saying it is less than.
It is. Okay.
Okay, so I will conclude with some perspectives. So the channel coding and the GC plus code and whatever I discussed today is part of the bigger picture. So the decoding pipeline in general, after you get your noisy data, involves clustering, alignment and consensus, and then channel decoding. We will hear more about clustering, alignment and consensus tomorrow with Dominique. And with the channel decoding, you do the inner decoding and then you do the outer. All I explained today is this inner part of the channel decoding. So I did not present a complete end-to-end solution that can be applied in DNA storage. I'm just saying one part of this pipeline I can use GC plus codes for. But what you use in other places is something else. So, and the take-home message is that in DNA data storage, addressing errors and biases algorithmically rather than biochemically offers major advantages in terms of the costs I talked about at the beginning, reducing costs. And also something to keep in mind is that increasing sequencing depth alone is sometimes insufficient to correct errors and is always resource inefficient, I would say. Why insufficient? Because you can have systematic errors, I explained. In that case, no matter how much you read, you cannot correct these errors. Why resource inefficient? Because when you use channel codes, instead of using 1 million reads to decode a certain file, you can probably do it with 10,000 reads, for example. That's using your resources efficiently and reducing costs in terms of speed and maybe money also. So the channel coding, I believe, has a strong potential to shape the future of the field. Like if we can have less expensive synthesis technologies that are more noisy and fast, and we can make them viable because we are compensating for the errors algorithmically, then that's a major advantage. And last thing, I want to use this opportunity to advertise for 2 posters tomorrow, which are unrelated topics to what I described today. As you may have noticed, the GC plus codes have some drawback in terms of complexity. If you have to guess a lot, then you have a high computational complexity. So to overcome this computational bottleneck, it's something we're working on, that my student Rami is working on, and he has a poster on that tomorrow. And another thing is that these 3 different steps for decoding do not necessarily have to occur separately. You can do stuff jointly. You can do the alignment consensus decoding steps in a single framework, which we call sequence reconstruction, and that also has benefits. So if you compare that to using aligners like Muscle or K-Align and then doing decoding versus designing the whole thing jointly, there are advantages that you can have. And that's what Sinan is going to talk about in his poster tomorrow. So that's all. Thank you.